So let's continue our study of asymptotic behavior. And before we begin, I'd like to apologize if you hear hammering, drilling, sawing, and shouting. They're remodeling the business downstairs, so sometimes it gets noisy. I hope it'll make it more interesting for you. As the gentleman in the Nerd Study video said, asymptotes are lines that the graph of a function gets closer and closer to. Now, he also said that the function never touches the line. And that is not true for horizontal asymptotes. It's true for vertical asymptotes. And it stems from the way that those our asymptotes are calculated. For vertical asymptotes, and I'm just going to abbreviate that, graph never crosses never touches the asymptote. Because the function is undefined. And that's because we find a vertical asymptote, which I'm going to abbreviate now VA, by seeing what numbers, what x values, make the denominator 0, but not the numerator. So we end up with some number divided by 0. And that can't happen. And we have a vertical asymptote, major break in the graph. And the graph cannot cross that line. Horizontal asymptotes, though, the graph may cross the horizontal asymptote. Because we're not going to be dividing by 0. To find the horizontal asymptotes, we look at the end behavior. As x approaches infinity, or x approaches negative infinity, do the y values seem to be leveling off to a particular number? And if they are, then that gives us a horizontal asymptote. So when you looked at the illustration already, a vertical asymptote here at x equals 1, apparently if you plug a 1 in the function, you're going to end up with some number divided by 0. And the graph cannot cross that vertical asymptote because the function doesn't exist when x equals 1. For a horizontal asymptote, though, we just want to see as the x's go out to negative infinity, lower and lower and lower, does it look like the y values are leveling off to a particular number? Or as x goes out to positive infinity, does it look like the y values are leveling off? For a horizontal asymptote, it doesn't matter what happens in the middle. All we're concerned about as x wings out to positive infinity, flies down to negative infinity, are the y values leveling off. And in both cases here, they are leveling off to y equals 3. Doesn't matter that it was going up to positive infinity here. As x goes out this way, what are the y's doing? Doesn't matter that it crossed the asymptote there. It's okay. Just what is happening in its end behavior in the graph. The second illustration, and this happens a lot with the trigonometric functions, which we'll study hopefully in March. The graph crossed this horizontal asymptote multiple times. Actually, it'll cross it infinite times. But as the x values get larger and larger and larger, the y values are getting closer and closer to the value of 1. So we would say that the horizontal asymptote is y equals 1. Okay, because the horizontal asymptotes are found as x goes to infinity or x goes to negative infinity, there can be at most 2 horizontal asymptotes. You can have infinite number of vertical asymptotes. Lots of places where a function's undefined, but cannot have more than 2 horizontal asymptotes. As x approaches positive infinity, or as x approaches negative infinity. Those are our only 2 choices. Whereas we can have multiple vertical asymptotes. And that's what was illustrated in the second sheet. We have 2 different, as x approaches positive infinity, and the graph crossed it here, and then is leveling off, we get one answer. As x is approaching negative infinity, we are getting a different answer. And the same thing happened on this second graph. Now the second graph, we would probably have we should have a vertical asymptote here at negative 3, because that would make the denominator be 0, but not the numerator. Same thing here, we should have a vertical asymptote at positive 3, because if you square that, subtract 9, you'd be dividing by 0, but it wouldn't make the numerator equal 0. A fourth difference between the two, vertical asymptotes, because they're vertical lines, their equation is x equals a number. And horizontal asymptotes, because they're horizontal lines, the equation is going to be y equals a number. And because they're lines, you have to write them as the equations of lines. So if we have the graph of a function, it's pretty easy to find the horizontal asymptote. We just look at the picture, see are the y values leveling off as the x's go farther to the left and farther to the right. But suppose we don't have access to the graph. Suppose they just plop the equation down. How are we supposed to find the horizontal asymptote? Well, one way, basic approach, is to just substitute larger and larger numbers in for x. After all, that's what the definition is as x is approaching infinity or as x is approaching negative infinity. So just plug in bigger and bigger x values. Are the y's leveling off? If they are, we have ourselves an asymptote. If they aren't, we don't. Now this can get really tedious, especially if you don't have a powerful calculator. Fortunately, for the types of problems we're working with, there's a beautiful shortcut. Like most shortcuts, it only works for specific cases. Case in point. If we have a rational function of the form f of x equals a polynomial over a polynomial. And we've been working with polynomials forever, it seems. No, only for a couple months. Then we can find the horizontal asymptotes just the horizontal asymptotes by comparing the degrees. I'm hoping you remember what the degree of a polynomial is. The highest power. So we're going to have three cases. If the degree in the denominator is greater than the degree in the numerator, the horizontal asymptote equals 0. For instance, if we had f of x equals 4x squared plus 3x minus 9, all divided by 3x to the fifth minus 20. So the degree on the denominator is 5, the degree on the numerator is 2. Now remember, x is approaching infinity. As x approaches infinity, 3x to the fifth is going to get much larger than 4x squared, much faster. Doesn't matter that we're subtracting 20. I mean, this is like when x equals 10 million. This minus 20 just fades away. Same thing in the numerator. The 3x minus 9 doesn't matter. It's just these leading terms here. So the denominator is going to grow much faster than the numerator. As x approaches infinity. Should have put that in the first part, I suppose. So as the x's get bigger and bigger, the denominator gets bigger and bigger, much faster than the numerator. And the whole fraction gets smaller and smaller. The fraction approaches 0. So the horizontal asymptote would be y equals 0. And if we wrote the equation, it should have the y in it. Well, that's one case, and you probably guess what the other ones are going to be. If the degree in the numerator is greater than the denominator degree, so for instance, our function is still the same numerator, but change the denominator a little bit. The same kind of thing is going to happen. As x gets incredibly large, as x approaches infinity, the numerator here is going to get larger much, much faster than the denominator. And the whole fraction is going to keep getting bigger and bigger and bigger. And we're talking huge numbers here. Like, let x equal 1 billion. 1 billion squared times 4, and then you divide it by 3 billion. Because 1 billion squared is going to have something like 18 zeros on it. So as x approaches infinity, the whole fraction just gets larger and larger. there is going to be no horizontal asymptote. The y values will also be approaching infinity. Okay, that leaves one more case. The denominator had the bigger degree. The numerator had the bigger degree. How about if nobody's got the bigger degree? If the degree is the same, oh, these are such long words. So they both have degree 2 in this case. The horizontal asymptote is going to be the ratio of the leading coefficients. Which sounds long, but it's really easy. So you have to remember what the leading coefficients are. They're the coefficients on the leading terms. So that would be the ratio, the 4 is the leading coefficient in the numerator. The 3 is the leading coefficient in the denominator. Now they're not leading because they're the first numbers. They're leading because they're the coefficient on the terms with the highest power. So if these things aren't in order, you'll have to pay attention. The leading coefficient is on the term with the highest degree. So that's just going to be the ratio of 4 to 3. So in this case, the horizontal asymptote is actually going to have an equation. It's going to be y equals 4/3. That horizontal line, this graph is getting closer and closer to. The degree in the numerator is higher, we don't have a horizontal asymptote. If the denominator is growing faster than the numerator, horizontal asymptote is y equals 0. So let's just look at a couple of examples, finding the horizontal asymptote. So if we have x minus 8 plus x to the 4th over x cubed minus 8, and I should have said f of x equals that fraction. Horizontal asymptote. We're just going to compare the degrees. So the degree in the numerator is not 1. The degree of the numerator is 4. The degree in the denominator is 3, which means as x goes to infinity, the numerator is going to be growing much faster than the denominator, and we would say that there is no horizontal asymptote. There's no horizontal line that the graph is trying to get closer to. How about if our function is this polynomial, divided by this polynomial. Now we know we could factor this and find holes in the graph and vertical asymptotes, but we're after the horizontal asymptote now. By comparing the degrees. The degree in the numerator is 1. The degree in the denominator is 2. Which means the denominator is growing much faster than the numerator is as x goes to infinity. So this function, this fraction, is going to get closer and closer and closer to 0. So the horizontal asymptote is going to be y equals 0. The next one's a little strange. Sorry. This one is not in proper format, but we can fix it with good old common denominators. We're going to put this over a common denominator so it makes it look like a single fraction. So if you remember that, we got to get them over the same denominator. And this is like 5 over 1. So we just need it to be over x plus 3 instead of over 1. And we can do that if we multiply the denominator by x plus 3 and multiply the numerator by x plus 3. Then everybody will be over x plus 3. So I have 2x over x plus 3. And we'll have 5x plus 15 over x plus 3. And that goes to f of x is going to equal 7x plus 15 over x plus 3. Okay, now it's looking like a polynomial over a polynomial, and we can use our nifty little rules. The degree in the numerator is 1. The degree in the denominator is 1. So the horizontal asymptote is going to be 7 over 1, or y equals 7. So that's a nice little shortcut. It's time for you to try it, please.